Hey guys, this is Srini and you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In previous tutorial, we talked about key point detectors and descriptors. And key points are regions of interest that can be used to compare a couple of images, let's say. And the detectors, as the name suggests, detect the key points, and the descriptors describe these key points. And there are detectors by themselves, there are descriptors by themselves, but most useful solutions would be a detector and descriptor put together into one. And SIFT, for example, SIFT is one such example. SURF is another example. But unfortunately, because of some patent issues, SIFT and SURF are no more available in openCV 3 or later versions. So we are going to use something called ORB, and we already talked about it in the last tutorial. And it's not a compromise because we don't have SIFT. In fact, when you look at some online feedback given about ORB, some people find it more useful than SIFT, in certain situations. But in general, ORB seems to be a very good alternative to SIFT. So we'll go ahead and use that. And in today's tutorial, let's look at an application where we have two images, one reference and one warped or deformed. And let's take the deformed and change it, transform it, stretch it to match or to register with the reference image. And this is probably needed for microscopy anyway, because most microscopes drift, especially the older ones, and especially if you are collecting images over a long period of time. So registration may be something that can be that you can find useful. So let's jump in and start writing our code. So if you look at the screen here, looks like we have the code left over from the last tutorial. And here you can see that we started off by importing CV2, which is openCV. And then we are reading an image, which is an image of a monkey. And we converted that image to grayscale. And we initiated ORB object. Okay, let's say we initiated ORB with 50 points. And then we applied detect and compute onto our original image. Okay, which means the result of this is nothing but a bunch of key points and associated with the appropriate descriptors. Okay. Now, then we used a function called draw key points, which is amazing because it draws these key points onto our original image to make it easy for us to visualize all these key points. So that's pretty much it. And the input for this one is our image itself and the key points. So if we go ahead and run this, so here is the image, our original image with a bunch of key points. Okay, so there are a lot of key points around here, and for whatever reason, ORB, this algorithm thought that, okay, these are the right key points for this image. And if you really would like to know why, that's when you have to dig a bit deeper to understand the math behind ORB, which is beyond the scope of this lecture, to be frank with you, which is beyond the scope of my knowledge at this point, because I haven't looked inside that box yet. Okay, so there's no point in talking more about that. So when I close this, on the right hand side in the variable explorer, you can see that the key points is nothing but a list of points. That's pretty much it. Okay, and our images are unsigned integers 8, and our descriptors are it's again a size of 47 by 32, 47 because it found 47 key points. Okay, so let's modify this code to get our task done. And by the way, let's define what the task is to begin with. Let's break it down into various steps so we know what steps we have accomplished and what we need to do. So step number one, of course, we need to import two images. Yeah, one is the deformed image and one reference image. So we need to import two images and then convert to grayscale. Yeah. So which we have already done here. So nothing new yet. And then we need to do our ORB. So let's just say initiate ORB detector. Okay, I don't know if they call it orb or just ORB, but I'm going to just say orb. Okay, so initiate orb detector, and then we need to do find key points and define or describe them. Okay, or descriptors. So all of these steps we have done it here. Okay, we just need to do that for 2 images. So once we get the key points and we have the descriptions for the key points, now we need to match them. Okay, match key points between the 2 images, nose to nose, ear to ear from this monkey. Yeah, we need to match these key points so we can apply another algorithm to transform them to match these 2 images. But first we need to match the key points, and for that what we are going to use is something called brute force matcher. Okay, so I'm going to talk briefly about it in a minute. So that's the algorithm we're going to use. Once the key points are matched, then we cannot assume that all these key points are good. Some may be mismatches. Some are these what do you call these? Let's just say that we need to extract the good ones from the bad ones. We need to separate them, and for that we need to we use something called RANSAC. This is pretty much standard. So this is nothing but reject bad key points. Okay, so that's what Runsack actually does. So matching the key points, and then subset of those, selecting the good ones from the matched key points, and once we have that, we're all set for registration. Okay, register 2 images, and for that let's use homology. Again, you can look up the what homology means, but it's literally 1 line in our code. But homology actually does a lot more. You know, it looks at a 2D plane and a 2D plane that's warped, and then tries to match these based on the key points that are defined in both of these images. So again, the advantage right now with Python is you don't need to understand to use them. You can look at the result and say whether it is good or bad. But if you understand the algorithm, it's even better, because now you can define the parameters instead of typing none everywhere. Maybe you can enhance your results, make them more appropriate and accurate by typing the right parameters in there, if you understand the algorithm a bit better. But let's go ahead and jump in. So I'm going to leave these 2 as is, and I'm going to add another image. In fact, instead of typing the whole thing, let me just go ahead and copy this and add another line, because we need 2 images. So since we are going to use image later, I'm just going to call this image1, im1, and im2. This is nothing but this other image. What did I call? Distorted, I think. Distorted.jpg. And the second image is monkey.jpg. Okay. So now our image, let me add another image. And by the way, let's, this is image to be registered. Okay. And this is our reference image, in case you wonder. Okay. Reference image. So now image 1 is im1. Okay. Image 2 is nothing but im2 converted to grayscale. Okay, these 2 lines, again, we know this is nothing but we are converting our input images into gray level images. And now we'll go ahead and initiate ORB exactly the same way, but instead of 1 key points and descriptor, now we have 2 of these. Yeah, so let me call this key point 1 and descriptor 1, and it's using image 1. That's fine. And key point 2, descriptor 2, and it's gonna use image 2 right here. Okay. Now this line, we originally had it to display, to draw the key points. So let's go ahead and do that. Image 3 is nothing but looking at image 1 using key points 1. Okay. And image 4, let's say we'll delete these lines. I just want to see if we are in the right track here. Image 4 is looking at image 2 using key points 2 and map key points 2 onto this image. And let's just call this, I'll just call this image 3. I'm not creative anymore. and copy this line, paste it here, and let's just look at image 4, image 4. So hopefully when we run this, if we haven't made any mistake, well, let me drag these two images from my other screen. You can see that it identified some key points in both images. In one image, it detected this mouth as a key point. In the other image, it did not. But the nose seems to be fine. The ear seems to be okay, meaning it detected the same key points in both images. So when we match it, maybe there are certain areas. That's when it uses the descriptors to match these two. Okay. So there seems to be one area right here that matches, and at least one right here that matches with this one. So there are a few key points that match. There are a few key points that do not match. Okay, so the next step is to do this matching of the key points. So let me go ahead and close this. And by the way, if you look on the in the variable explorer, again, the descriptors are, we already talked about what these descriptors are, so you can actually see nothing but bunch of arrays. Okay, some are lists, some are arrays, and this is a list. The key points are all bunch of lists. Okay, so now the next step, once we have this, let's create some room over there. So now that we have done the key points, next step is match the key points. This is something we haven't done before, and we're going to use brute force matcher. What does that mean? I think I searched for it, and let's go back and look at the so here is some documentation, and again, the reason I'm going through the exercise is it may be a bit difficult to follow this documentation. So if you follow the example, you should be able to repeat what I'm doing. So we are going to use something called descriptor matcher. So cv.descriptor matcher underscore create. Yeah, cv.descriptor matcher underscore create. And in the parenthesis, we'll do cv2.descriptor matcher, and we are going to use brute force hamming. Okay, look at again the documentation if you have any questions, but let me go ahead and type this. So we're going to do matcher. Okay, so one thing you need to, and by the way, I should have explained this, what a brute force matcher does. I took some notes here, so I don't forget talking about it because this is a long topic. It's easy for me to forget things. So let me repeat what I've written. Brute force matcher takes the descriptor of one feature, okay, in the first set. Okay, so it takes the, let's say it identifies feature 1. It takes that descriptor, okay, in the first set, because we have two sets here, image 1 and image 2, right? Descriptor 1, descriptor 2. It takes that from the first set and is matched with all other features in the second set, okay, and then does some distance calculation. Okay, so again, and then let's see how to implement this. So just like we created this orb, if you want to call it an object, just like we created this orb, I'm going to create a matcher. Okay, in many ways, this orb or SIFT or whatever you end up using, in the implementation wise, it's very similar, our matching is very similar to that. So again, hopefully it makes sense once we do that. So just like I described or initiated orb, let me initiate matcher. Okay, and the way we do that is cv2.criptor. I like to spell it out, so I spell it out correctly. Matcher underscore create. Okay, and I think C is not uppercase, underscore create, cv2 dot and descriptor matcher BRUTEFORCE brute force HAMMING. Okay, I think that is what it is, and in fact one way to find out is, let me just run up to that point. No errors, so I haven't made any spelling mistakes here. Okay, so now I define this. Now let's do the match the descriptors. Okay, so now we need to go back and look at our descriptors. And our descriptors are descriptor 1, descriptor 2. Okay, so I'm going to match these two descriptors using the matcher that I just created. Okay, so the way we do that is matches, let's say my matches between these two is equal to matcher okay, which we just defined here, dot match from descriptor 1, description 2, and the other parameters I'm just going to say none. Okay, again, let me run until this point, so if there are any bugs I can find out. Yeah, that obviously that's an easy one to fix. Okay, so let's go ahead and run this. Everything seems to be fine, so let's go ahead and move on. So far we have created the key points and associated descriptors. Now, once we have the descriptors, we are matching the descriptors between these two, and the result will go into matches. And if you look at matches here, this is nothing but a list just like key points. Again, like I said, from an implementation point of view, I see these matches and the key points and descriptors to be very similar in terms of how we write the code. So matches is nothing but our matcher that we defined, dot match, and it's matching between the descriptors that we have in 1 and 2. And they're labeled, and the output is a list. Okay, so this is our matches. Now, let's actually sort these based on the distance transform. Like I mentioned, it actually calculates some sort of a distance, right? So let's actually sort them based on these distances. So what I want to do is I want to update my matches list by sorting, okay, and matches. And by the way, how do I know how to do this sorting? I looked it up online, and then you can actually see, for example, I mean, if you do this again every day, you should know this, but the way you can actually do this sorting is, for example, if you have a dictionary, I guess, right here, or an actual array right here that has student John, whatever, A, and 15. Yeah, looks like 15 is the age right there. So student, another name, and whatever the grade, I guess, you know, they get, and then the age. And sorted, how do you sort them based on their age? And here is the implementation. Student objects, which is nothing but this entire thing. Yeah, key equals to lambda student, yeah, and student dot age. Okay, so we'll just follow pretty much the same convention to do our sorting, except instead of age we have distance here. Okay, so let's do sorted matches. Key equals lambda, okay, x dot distance. Okay, again, this one line itself you can just take half an hour to completely understand and master using various ways. Okay, and again, the intention of this tutorial is not that, but please do that. Please do that exercise. So when I run this, let's see, no errors, so that part is okay. So we are actually running fine, and the matches is again a list of the various matches. So I'm still getting a list back, so which is good. Okay, so now that we have the sorted list of matches, the next step is the identifying. I'm looking at, again, my notes. I can go back here and basically look at match key points. We did that. And let's reject the bad key points now. Okay, I should have included the sorting key points as part of our list, our steps, but that's okay. Let's, I'm actually thinking whether we should draw the matches before we go ahead and do something else so we can see how the matches look like. Let's go ahead and do that, because that way we can see the implementation. Again, the reason I want to show you this is, just like we did the draw key points before, there is something called draw matches, luckily. So we don't have to do a whole bunch of stuff to just show these matches. So let's go ahead, and we just need one line here because the matches we can show both images. Let's leave it to image 3. Let's not worry about it. Instead of draw key points, like I said, this should be MATCHES. Draw matches, and image 1, KP1, and the other one is image 2, KP2. Okay, and let's instead of I'm thinking let's actually look at only the first 10 matches. Okay, There you go. So what this does is it's going to show us matches. Okay, it's going to show us matches between image 1 and image 2, overlaying key points 1 and key points 2, and you'll see how the result looks like. So when we run this, let me drag it here, and you see these are the top 10 matches that are, again, we sorted them. We sorted these, so it's actually showing the top 10 within our sorted list. Okay, and it's actually drawing the keywords, key points. They look to be pretty good, actually. You see the one from the eye going to the eye, the one from here going to this neck area, the one from these legs going here. So that's not bad, actually. That's very good. If we actually do use these key points to transform the image, I'm pretty confident that we would get a pretty decent result. Yeah, this is, again, an easy way of looking at these matches. So again, it's draw matches, just like draw key points. Okay, so let's now use these key points to register these two images. And I talked about homography. I was thinking about whether I should talk about homography, but why not? So homography, like I mentioned earlier, if you actually have, I believe they described it. So if you have any two images of the same planar surface in a space, they're related by homography, okay? So you can take these points. Now we have these key points that are related in space between these two images. We can use homography to match this, okay? That's why we are going to use this homography. And so we are going to start this by extracting the good key points or good matches like I mentioned before. Okay, how do we do that? And for that, it requires Runsack. Again, let's look at the. So I found I didn't find like a good official documentation for Runsack, so I just Google searched and found something here. Again, you can screen grab the URL right there. It basically talks about it stands for random sample consensus, and in computer vision it's used as a method to calculate homography between two images. So Runsack, it's almost like a pre-processing before you do homography. Okay, and I looked at code provided here and a whole bunch of other places. And then I summarized it to as simple as I can for our purposes. Okay, so there are a bunch of examples right there. So go ahead and look at this at leisure. And the other one, drawing function of key points. Again, draw matches. I already talked about draw matches. I just opened the page so you can see how the implementation can look like if you want to do it yourself. Okay, so let's jump in. So first, we need to do this Runsack thing. So, so what we do is it needs all the key points indexed. So I'm going to create one list called points1. Okay, equal to. Did we import NumPy? Yeah, np. And all I'm going to do is start off with a empty or not empty, an array that's filled with zeros, and then replace the zeros with the key points that are indexed. Okay, so first let's start with zeros, and how long do I want this list to be? It's as big as our matches. So in this example, 47. Okay, so that and then 2. Okay. And the data type apparently needs to be float 32. So let's go ahead and type dtype equals np dot float 32. Okay. So this is nothing but I'm creating a whole bunch of points. I'm not sure if this makes any sense to you. All I'm doing is, let me actually go open another blank page so I can show you what I mean here. So for example, import numpy as np. All I did is points1 equal to np dot zeros, and instead of instead of 47, I've typed len of matches, which is nothing but 47. So let's just take an example of 10 and 2. Okay, and then let me type d type, okay, equals np dot float 32, and let's just, where am I, float 32, and let's just print our points 1. I'm doing this so you can see exactly what to expect in the other code, okay? So when we do that, it actually created 10 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? 10 of these zeros. That's pretty much it, of float 32. So if you look at points 1 here, points 1, float 32, type 10 by 2 size. So that's what I'm defining here. So the size of this array is 10 by 2 and filled with zeros, okay? So now let's go back to our program. Points 1 is nothing but an array of whatever this length is. It detected 47 key points, so 47 by 2 of float 32. That's all I'm doing here, okay? And the next line is points 2. So let's just, so points 1, I'm hoping to correspond those to my image 1, points 2 correspond to our image 2, okay? And this is points 2 also should be pretty much the same. There is no difference because this is all a bunch of zeros. And now let's fill this, okay? So for that, I'm going to use our enumerate function. Again, enumerate, I don't know if you remember, I'm not even sure if I covered this. Probably I did. Let's say before jumping on, a quick detour, okay? So let's say our 30, 40, that's fine. So let's say our array, you know, has 4 entries there. And if I say for C, comma, value in enumerate, this is one way of kind of unwrapping this, okay? What do we want to do for these values? Let's just go ahead and print C and val so you see exactly what I'm talking about, okay? So if we run these lines, you should see that for C goes from 0, 1, 2, 3, 4, right? And then value is nothing but unwrapping the value from inside this L array, okay? Now, the first one value for 0 corresponds to 10, you see? 20, 30, 40. So I'm just unwrapping this. So that's exactly what I'm going to use here. So for I, okay, this is again going from 0, 1, 2, 3, 4, match, okay, a new variable I just defined in enumerate. And in what list are we enumerating? And by the way, I may have called the previous one array. Well, it was basically a list I just showed you, okay? For I match in enumerate, which is our matches, okay? What do we want to do within this? So my points 1, okay, and I, which is 0, to all of these, I'm going to replace them with KP. What did we call it? KP, right? Key points? Yeah. So our key points match. And this is where I would like to explain in a second. So idx.pt. I looked at how they have implemented this Runsack thing online, and then identified that a few places this is exactly how they have defined their points. And my understanding of this is this one gives index of the descriptor, okay? It gives the index of the descriptor in the list of our query descriptors. Our query descriptors are the ones from our image that we would like to morph, for example. So for image 1, it says query here, right? So it's going to index of the descriptors in our query descriptors. The other descriptors would be, we can call it the train descriptors. That's the training descriptor. That's what we use for training. Okay, if it is machine learning, the image that we know is good is the training image, and the other image is our test image or query image. Okay, so similarly, I'm going to define my points 2. Okay, and again, same thing. Let's go ahead and do this. Equals to key points 2. Okay, fill it with key points 2 and match train ID X. Okay, that's a key point. Again, this gives the index of the descriptor in the training descriptors. Okay, so now we have these 2 points, and again, I don't want to confuse again. You can see my lack of knowledge in this part right here, especially I should accept that in query and train IDX, you can go search for it, but almost think of this as the routine that you do before you apply your Runsack or your homography. So if you search for homography and if you look at how it is implemented, there are many ways, and it's so easy to get lost reading all of that stuff. And this is my essence of what I have learned online. What I have learned online is to extract these points to begin with, okay? To extract these points. To do that, I started off by creating empty lists. This part, obviously, I'm very comfortable with, creating empty lists with all zeros. And then fill those empty lists. Yeah, that's what exactly I'm doing here. Fill the empty list with the key points. So all I'm doing is unwrapping the key points. So if I let's print points 1 right now, okay? It's been a while since we checked how the program is working. So these are all the points now, okay? So points 1 is nothing but 95. Unfortunately, we don't see what the key point values are here, but then all it's doing is unwrapping the key points 1, okay? And in fact, let's do points 1, and let's also do print. Let's do what happens when we do kp1, okay? Let us run this. So, oh yeah, the key points are actually stored, so you cannot see the values. Sorry about that. But anyway, so we are unwrapping those key points and assigning those values into our points 1. So this is nothing but the coordinates of, you can see here 95.04, 73.44. So it's almost like, think of these as the points. Where is it again? Sorry for spending too much time here. This is very important. So you can see that this is a 47 by 2 matrix, 47 points, okay, by 2 matrix. So these are all the coordinates of our key points in the first image and in the second image. It's a bit encouraging to see that the first coordinate between the first image and the second image is very close, very similar. Yeah, very close to each other, although I have warped the image, so I'm not sure if that's a good sign or bad sign. Anyway, so the point here, again, I've been belaboring this for the last 5 minutes and haven't done anything, but hopefully this makes sense. Points 1 and points 2, nothing but the bunch of coordinates of our key points that we have identified. And they obviously go in as parameters into whatever we are doing next, which is nothing but doing our homography. And you can look online again how to apply this homography in openCV. Initially, I thought of not doing this at all because it looked very difficult, and I have never done this before. So, but it took a while for me to figure out, oh, this shouldn't be that difficult. It's pretty straightforward. All we are doing is, extracting a homography matrix, I believe, when we do estimated homography, and then the mask. And how do we apply this? CV2 and find homography, find homography of between, I should say, points 1 and points 2, okay, CV2 dot RANSAC. So this is the parameter, and this one actually, what it does is, I believe it's a program. Did I actually pull up the documentation for Runsack? I think it's better to look at this, and it's an abbreviation, and as a method to calculate. I don't think this person explained exactly what it is. Maybe he did. But so Runsack method is nothing but a loop, select 4 feature pairs, compute homography, compute inliers. Yeah, he did mention about the inliers and outliers, right? So Runsack is a method. My understanding is it's a method of detecting the outlier points and then keeping only the inlier points, the good ones. So remember, we wanted to separate the good points from the bad points. Exactly. This is how we are doing that. So that's pretty much it. So by the way, we haven't. I mean, we generated this H. Let's run this. Let's run this and make sure it's working, and then we can continue. Okay. So it's working fine. And if you look at what H is, it's a 3 by 3. It's a 3 by 3 matrix. Okay, which is what you can actually call you can call it like a homography matrix if you want to call it. So obviously you know where we are heading. So we can take that H value to do some sort of image registration. Okay, so that's our next task. So next I'll just call this use homography. Okay, so our next step is to use this into our homography. So for that, we need to know the height and width as of our image as input parameters to this homography. So we may as well assign parameters height, width, and we may not have the. Let's go ahead and do the channels im2.shape. Okay, so my height is whatever the height is of my image. I just said im2. It doesn't matter, image 1 or image 2. Well, actually it does matter. Image 2 is my reference image. That's why I'm going to use my image 2 here. Okay, so number of channels, and I am 2, so the number of channels should be 3 in this case. Okay, I'm not doing this on a grayscale image. Anyway, so now that we have it, let's go ahead and say our image 1 registered equals to CV2 dot. And there is another one that we can look at. Geometric image transformation. This is what I'm going to use, warp perspective. Okay, so warp perspective is the one that I'm going to use to do our image registration. So this is W-A-R-P-P-E-R-S-P, warp perspective, and I'm going to use image 1, H, width, height. Okay, so width and height, I think we need that. Width and height, image 1, and height, that hopefully should help. Let's go ahead and delete this line and CV registered image. Okay, and our registered image is our M1 REG. Let me confirm this one more time. Okay, so image 1. So I just want to double check that our image 1 is the morphed image. Yeah, that's a distorted image. We need to we need to undistort, or we need to register that with our reference image. Okay, so M1 and H using this homography matrix, and my width is whatever the width is, my height is whatever the height is of this image. Okay, so unwarp this image to this width and that height. Okay, these width and height are coming from image2.shape, right? So this is our reference image. Okay, unwarp them to the same size as my reference image using this homography matrix and using that image. So this is it, moment of truth. Let's go ahead and hit this, and this is the image that we are looking for. In fact, let's go ahead and do cv2.imshow. This is our key point matches. Okay, and which one did we use? It's called image 3, right? Or did we delete that? I think I deleted that, so that's fine. It doesn't matter. My image 3 equals to, I'm glad I've written down what to show and what not to. So image 3 is draw matches. Yeah, if you remember that, between image 1, key points 1, image 2, keypoints 2, and we showed the first 10. And the way we do that is this and none. I believe this should do. None. Okay, let's see if this works. Image 3. Let me close this other window and do this one more time. Has no attribute draw matches. Image 3 equals to CV2. Obviously, it doesn't have that. DRAW matches. Let's run this. Okay, so here is our matches. Okay, here is the summary. Our original image 1, image 2, which is our reference image, key points that are matched, and image 1 stretched or transformed by using the key points here, okay, and using the homography matrix that we just calculated, and it unmorphed it, and it looks like the original image. Okay, so you can do pretty much the same thing on your microscope images. In fact, I almost recorded this video using a couple of microscope images, but the key points there are not that obvious when you see it. You know, it was a bunch of cells here and there, and by matching them, it made it a bit confusing. That's why I used an example of a monkey where you can clearly separate eye from the ear and everything else, so you can see how different regions are used in doing this registration. So let me summarize this one last time, and by apologizing for any areas where I may have spoken at length, but for good reason and good intentions. Okay, so I hope you appreciate the intentions, if not the reason. So we started off by inputting two images. One, the image that need to be registered, and two, the reference image. Okay, and then we converted them to grayscale and initiated the ORB. If you somehow working on older version of openCV, you can use SIFT for this, SIFT. So in that case, you initiate SIFT instead of ORB. That's the only difference. Okay, we initiated that, and then we detected and computed the key points and descriptors. Okay, so once we have the key points and descriptors, we tried to match them. And how did we match them? We matched them by creating a matcher object, let's say. I mean, technically this is not an object in programming, but I'm just calling it an object, so don't confuse this with object-oriented programming. Okay, so we created a variable, let's say, called matcher, which is nothing but descriptor matcher create. Okay, it's using this function and the algorithm of brute force Hamming, and with that we are actually matching descriptors 1 and descriptors 2, which means it's using the information from descriptor 1 and descriptor 2 to create a list called matches that has all the information about these matches, that contains the matches. Then we sorted these matches based on the distance, because this is nothing but a distance map, right, when we do calculated this. So we use the distance to sort this, and we created points 1 and points 2, started off by a list of zeros each, and then we replaced the zeros with the key point coordinates that we unwrapped using our enumerate method. Okay, so for I match in enumerate, so it goes through key points 1 and key points 2, and then indexes them as query or train. Okay, and then puts them in points 1 and points 2. Once you have that, then we did find homography. Okay, and then Runsack inside the parameters here, and what Runsack actually does is it throws out the outliers, only keeps the inliers. That's the whole point of this. That's pretty much it. Okay, using that, it calculated the homography matrix, okay, which is almost like a transformation matrix. You want to go from this image or this matrix to the other matrix. What do you want to multiply this matrix with to get to this other image? That's what we calculated here, okay, the homography. And then we realized that to apply this, we used warp perspective, that uses homography, that takes in the homography matrix as an input, but also the other inputs would be what is your original, I mean, the image that you want to transform, and to what width and height do you want to transform. So for that, we kind of found the height and width as part of our image2.shape. And that's pretty much it. And this is the one line that actually does this registration step. And then we visualize the registered image and the key point matches image to try to get some sense out of it. So this is, again, this appears to be a bit complicated, but if you go through step by step, and if you understand every little step, then it's everything makes sense, okay? So I hope you found this useful, and I really hope that you can use this for your own research purposes. And I went through this and I scrolled through this a few times, and in fact I'm going to freeze the screen by zooming out a little bit so you can freeze the screen and look at the code. And if you want the original code, just drop a line to me, multiple ways of getting hold of me. Leave a comment in under this video, but anyway, if you want the code, please let me know. Otherwise, I really appreciate you watching this entire video patiently for about 46 minutes. And if you like it, just press like and subscribe to the channel, which keeps me motivated to make more such videos and do a lot of research on your behalf to summarize things that I find online and relate to microscopy in a way. Okay, thank you very much, and let's meet again in the next tutorial.